Consider an archer aiming for a bullseye. He or she pulls back the bowstring and releases. This makes the arrow fly with great speed and strike on the target. Why does the arrow fly when the stretched string is released? Let's find out. There is a continuous movement of rocks inside the Earth's crust. This makes the crust non-uniform by creating discontinuities and fractures. These discontinuities or fractures on the Earth's surface are called fault lines. They possess a tremendous amount of potential energy. Occasionally, in different parts of the world, the Earth feels the need to release this energy by readjusting the fault lines. This release of energy is what causes earthquakes and volcanic eruptions. So, potential energy can be defined as a stored energy that an object has due to its position or configuration. It has the same unit and dimensions as that of kinetic energy. A body will always try to decrease the stored potential energy by releasing it in the form of kinetic energy. Let us consider gravitational potential energy to understand the idea of potential energy in more detail. We have a ball of mass m placed at a height h above the Earth. The gravitational force on the ball by Earth is minus mg. This means that the Earth pulls the ball to its center with a force equal to the magnitude of mg. Therefore, the same amount of force must be applied to the ball to displace it to a height h above Earth. This means that a work is done in order to displace the ball into the height of h. This work is stored in the ball as potential energy. Gravitational potential energy is a function of height and it is denoted by V of h. It is the negative of work done by the gravitational force in raising the object to that height. The negative of the derivative of gravitational potential energy gives the gravitational force. Minus d by dh of V of h is equal to minus d by dh of mgh, which is equal to minus mg. The negative sign indicates that the gravitational force is downwards. When the ball is released, it falls down with an acceleration minus g. So, the velocity of the ball is just before it hits the ground can be given by the kinematic equations v square minus u square is equal to 2as. But here u is equal to 0, a acceleration due to gravity and s is equal to height. Now, multiplying both sides with half times m, we get half mv square is equal to mgh. This means that the potential energy stored in the ball gets converted into kinetic energy as it falls to the ground. Potential energy gets stored in a body only if some work is done against the force. In the beginning, we have considered the example of an archer shooting an arrow. Here, she does some work on the bowstrings by pulling it backward. This work is stored in the string as potential energy. When released, meaning removal of external constraints, the string moves forward pushing the arrow in front of it. That is, the stored kinetic energy gets converted into potential energy. Mathematically, the potential energy V of x is defined if the force F of x can be written as f of x is equal to minus d by dx of Vx. This means that integral xi to xf f of x dx is equal to minus integral vi to vf v of x dx, which is equal to integral xi to xf f of x dx is equal to vi minus vf. This means that the work done or potential energy due to the force only depends on the initial and final positions of the body. That is, the work done by the force is path independent. Such forces are called conservative forces. Another wonderful example of stored potential energy is a waterfall. The water at the top has high gravitational potential energy. As it falls down, the potential energy gets converted into kinetic energy, which makes the water flow with great velocity. The same potential energy concept is used to create electricity in hydroelectric power plants, where water is stored in a reservoir behind the dam. Let us end this session with a question. Throughout this session, we have mentioned that potential energy is converted to kinetic energy. Why or how does this happen? Are potential energy and kinetic energies different sides of the coin? Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.